The systems we rely on every day are built on a fragile foundation of trust. We trust our operating systems. We trust the hypervisors that manage our cloud servers. We trust the system administrators who hold the keys to the kingdom. But this trust is often misplaced. Malicious software can burrow deep into the kernel, becoming an invisible spy that sees everything. A compromised administrator, whether through coercion or carelessness, can access any data on a server. The operating system itself, a sprawling metropolis of millions of lines of code, is riddled with undiscovered vulnerabilities. When the very platform you run your software on is untrustworthy, no amount of application-level security can truly protect your most valuable secrets. This is the fundamental problem of modern computing. For years, we have tried to solve this with software. We build firewalls, intrusion detection systems, and antivirus programs. At the heart of Intel SGX is the concept of the enclave. An enclave is a private and isolated region of memory protected by the CPU. When a program creates an enclave, it loads specific code and data into this protected area. From that moment on, the CPU enforces strict access rules. No other software on the system, the operating system, a hypervisor, the BIOS, system management mode code, can read or write to the memory inside that enclave. It is a black box, visible only to the code running inside it. This provides a powerful guarantee of confidentiality and integrity. This protection is not based on software permissions or privilege levels. It is enforced by the processor's microcode and hardware logic. The CPU acts as the guard at the gate. Any outside attempt to access enclave memory is blocked by hardware, which returns an error or garbage data. Even if an attacker gains root access and controls the operating system, they still cannot peer inside the enclave. They cannot inject malicious code into it. The code loaded initially is the code that will run, and the data it processes remains secret. But understand what the enclave does and does not protect. The protection an enclave provides would be incomplete if an attacker could simply physically access the computer's memory chips. If the data were stored in plain text in RAM, an attacker with physical access could use hardware probes or a cold boot attack to freeze the memory modules and read their contents directly. This would bypass all of the CPU's access control mechanisms. To defend against this class of threats, Intel SGX includes a feature called the Memory Encryption Engine, or MEE. The MMEE automatically encrypts all data leaving the processor package for main memory and decrypts it upon its return. This process is transparent to the software running inside the enclave. This memory encryption acts as an invisibility cloak for the enclave's data. When the CPU needs to write data from the enclave to RAM, the MEE encrypts it using a key that is randomly generated and stored securely within the CPU itself for each power cycle. This key never leaves the processor boundary and is inaccessible to all software, including the enclave's own code. When the CPU later needs to read that data back, the MEE decrypts it after it has been fetched from RAM and before it is used by the code inside the enclave. From the perspective of the code, it is simply reading and writing to memory as usual. But from the perspective of an outside observer looking at the memory bus or the RAM chips, the enclave's contents are just an indecipherable stream of encrypted gibberish. This protection is absolutely critical because it extends the trust boundary from just the CPU's internal registers to the physical memory modules. It ensures confidentiality even in the face of sophisticated physical attacks. Without memory encryption, an attacker who could steal a server could potentially recover secrets. With memory encryption, the data on the RAM sticks is worthless without the ephemeral key locked inside the original CPU. Having a secure enclave is powerful, but its utility is limited if you cannot be certain that it is what it claims to be. Imagine you are a client wanting to send your private financial data to a service running in the cloud. The service provider tells you they are using an SGX enclave to protect your data. How can you be sure? How do you know they are running the correct, unmodified version of the approved software inside that enclave? How do you know it is a genuine Intel SGX enclave and not some software emulation designed to trick you? This is the problem that remote attestation solves. It is a cryptographic protocol that allows a hardware enclave to prove its identity and the integrity of its code to a remote party. The process works like a sophisticated digital handshake. Client requests quote. Server enclave generates report and signs. Server sends quote to client. Client sends quote to Intel Attestation Service. IAS verifies. Client establishes secure channel with enclave. First, the client's application asks the server's enclave to produce a quote. To do this, the CPU generates a report that contains a cryptographic hash, a unique digital fingerprint, of the code and data loaded into the enclave when it was created. It also includes any data the client wishes to embed in the report, like a public key for establishing a secure channel. This report is then signed by a special attestation key that is unique to the specific CPU and fused into the silicon during manufacturing. This signature can only be created by genuine Intel hardware. This signed report, now called a quote, is sent from the server back to the client. The client cannot verify this quote directly, so it forwards the quote to a public Intel attestation service. Intel's service verifies the signature and confirms it was produced by a genuine Intel CPU with SGX enabled. The IAS then sends a confirmation back to the client, attesting to the authenticity of the enclave. The client compares the code measurement from the quote with the expected measurement. If they match, both parties can trust each other and use the embedded public key to establish a secure, encrypted channel. Any secrets exchanged, API keys, user data, session credentials, can only be decrypted inside the secure enclave on the server. While Intel SGX provides a paradigm-shifting security capability, it is not a silver bullet. The technology comes with a significant list of limitations and risks that developers must understand and mitigate. Limitations. Risks. Ignoring these constraints can lead to a false sense of security and systems that are vulnerable in subtle and surprising ways. The first and most widely discussed limitation is the constrained memory size. The enclave page cache is a small, reserved area of physical memory where encrypted enclave pages reside. In early SGX versions, this was limited to 194 megabytes. That made it impractical for large memory footprint applications. Newer hardware has increased the limit, but it is still a finite resource requiring careful management. A second major constraint is the enclave's isolated nature. By design, an enclave cannot make direct system calls to the OS. It cannot open a file. It cannot send a network packet. It cannot get the current time without help. To do any of these, the enclave must exit and ask the untrusted host application to act for it. Those transitions are a performance bottleneck, and they expand the attack surface. Every piece of data crossing that boundary must be treated with suspicion. An attacker controlling the OS could provide malicious inputs. They could modify outputs, or refuse to service requests. Those behaviors can lead to complex denial of service vulnerabilities. Third, and perhaps most insidiously, are side-channel attacks. They don't break SGX cryptography directly. They exploit indirect information leaks. Attackers observe memory access patterns. They watch cache usage. They measure execution timing. They even measure power consumption. From that, a sophisticated attacker can infer secrets processed inside the enclave. Researchers have demonstrated attacks like Spectre, Meltdown, Foreshadow, and many other published attacks. Intel has released hardware and software mitigations, but the threat remains. Defending against side channels requires specialized, non-intuitive coding practices. For example, writing constant-time algorithms that avoid secret-dependent branches, and avoiding secret-dependent memory lookups. Given the power and the perils of SGX, developers cannot simply port existing applications and expect them to be secure. Building a robust SGX application requires a deliberate and security-first design philosophy. The primary rule is to minimize the trusted computing base. Your enclave should contain the absolute minimum amount of code and data necessary to perform its sensitive function. Do not put your entire application inside an enclave. Instead, identify the specific secrets and the precise operations that work on them. Is it a single signing key, a machine learning model, a proprietary algorithm? Isolate that component and build the enclave around it, leaving everything else, user interface, network logic, file I/O, in the untrusted part of the application. Next, meticulously design the interface between the trusted enclave and the untrusted world. Define a minimal and explicit set of functions. Every input must be treated as potentially malicious and rigorously validated before use. Pointers passed into the enclave must be checked to ensure they point outside. Be skeptical of anything the host provides in response to an O call. The OS can lie about the time, the contents of a file, the success of a network operation. Intel SGX represents a monumental step forward in the quest for secure computation. It provides a hardware root of trust that allows us to execute code with confidentiality and integrity, even on a completely compromised system. It fundamentally changes the security model, moving the foundation of trust from fallible software to immutable silicon. Through remote attestation, it enables trust in zero-trust environments, unlocking new possibilities: secure cloud computing, data privacy, digital asset protection. But this power is a double-edged sword. SGX is not a magic wand that instantly makes insecure software secure. It is a highly specialized tool with a steep learning curve and sharp edges. The limitations are core design constraints: small memory footprint, inability to make system calls, threat of side channel attacks, demanding a new way of thinking about software architecture. A poorly designed enclave can create a brittle boundary and a false sense of security. Responsibility shifts and concentrates inside the enclave. Choose SGX when protecting a small, well-defined set of high-value secrets or operations. Single cryptographic key, password manager's master key, signing logic for a blockchain transaction. SGX is an excellent fit. If your goal is to secure a monolithic legacy application with a gigabyte-sized footprint, SGX is likely the wrong tool. The re-architecture effort is enormous and likely to fail. The final takeaway is cautious optimism. SGX is powerful but must be wielded with expertise and discipline. Trust the hardware, but verify everything. The ultimate security still rests in the quality of the code you write.